Hello, and thank you for listening to my virtual presentation for AGU 2020. My name is Andrew Davis, and today I'm going to be talking about superparameterization of Lagrangian sea ice dynamics using the Boltzmann equation. I'd like to begin by acknowledging my collaborators. This, of course, is me, Andy Davis, and these are my collaborators, Demetrius Giannakis, Georg Stadler, Sam Steckman, and Georgi Manchurian. So we think of Arctic sea ice as being broken up into discrete chunks of ice, which are called ice flows or just flows. And mathematically, the way we model sea ice is using two potentially very different approaches. On the one hand, we have continuum models here, which model average quantities, such as the thickness averaged over some representative area. And this type of approach is very effective at a large scale, but it can't capture the small scale dynamics because we've averaged away those effects. These models also require a non-physical constitutive law or effective viscosity, which parameterize the interaction between the flows within these representative areas. On the other hand, we have discrete element models which model individual flows, and because we're modeling things on the flow scale, these models are very effective at modeling small scale dynamics. However, they quickly become computationally intractable for large scale, so basin scale dynamics, because we have to track the potentially thousands or millions of flows in the entire Arctic basin. We also need to attach to each one of these flows additional models for melting and freezing and flow deformation and fracture, which just adds a whole other layer of complexity. So the goal of our research is to derive a kinetic model which takes into account this flow-flow small-scale interaction, but generalizes or uses that within a hydrodynamic approximation or a generalization of the hydrodynamic approximation so that we can apply it at the large scale. So we are going to use the Boltzmann equation to model the kinetic behavior of sea ice dynamics on the large scale. The Boltzmann equation is defined in a coordinate system that has three parts. The first is time, because of course ice is dynamic. The second is space, where x is just some physical location in the Arctic or whatever basin that you're interested in. And the velocity coordinate v is a little bit different than in typical models for sea ice or many other things, where instead of the velocity being an unknown field that we have to evolve, we now incorporate the velocity as part of our coordinate system. So we're going to model sea ice using a probabilistic model where we've defined pi, which is a joint density or a joint probability distribution over the spatial coordinate x and the velocity coordinate v, where pi is basically the probability of observing ice at location x with velocity v. We can decompose the joint density pi into the mass density, which is the marginal density, where we've integrated out the velocity coordinate. And this mass density basically says if we have some subset of the domain E, we integrate over it, this integral is the amount of ice that's contained within E. So if E were, for example, the entire domain, then this is just the total amount of ice in our simulation. The second distribution here that we've decomposed our joint density into is the conditional distribution over the velocity coordinate. This velocity density basically says at some given point x, this is the probability of observing ice at that location with velocity v. And of course, all of these densities can evolve in time. And we do this evolution using the Boltzmann equation, which is this equation here at the bottom, which basically says that the evolution of this joint density depends first on advection in the spatial coordinate, and this advection is advected by the velocity. And then the second term here is advection in the velocity coordinate, and advection in the velocity coordinate is due to this external acceleration, which is some known and prescribed field, which represents acceleration due to interaction with something like the ocean or the atmosphere. And then on the right-hand side, we have a collision operator, which basically is a rearrangement of this density function due to flow-flow interactions, which are colliding with each other. And then this epsilon is some non-dimensional parameter, which basically weights how important the collision operator is or how important flow-flow interaction is for these dynamics. So now that we have the Boltzmann equation to model the large-scale kinetic dynamics of sea ice, we now need to derive the macro-scale conservation equations. And what I mean here by macro-scale are a set of equations that only depend on the spatial coordinate x and don't explicitly depend on the velocity coordinate v. This top equation here is the mass conservation, which we've derived by integrating the Boltzmann equation with respect to the velocity v. This mass conservation equation has a time derivative for the mass density, and then additionally, as you would expect, an advection term where the mass is advected around the spatial coordinate by an expected velocity. This expected velocity is the first moment of the conditional density function over the velocity coordinate. This expected velocity, the macro scale velocity, can depend on the spatial coordinate x because this probability density function is conditioned on the location x. The second conservation equation is the momentum balance equation, which again has a time derivative term and also an advective term. This advective term is defined by a flux matrix, is here in the parentheses. The first term of this flux matrix is exactly what you'd expect. It basically says that the momentum is advected by the expected velocity in the spatial coordinate. The second term of this flux matrix, however, is the covariance of the conditional density at this location x. This is very similar to a more traditional hydrodynamic model. In this type of hydrodynamic model, the sigma would be either parameterized by an effective viscosity or maybe a constitutive relationship which relates stress and strain. But in our kinetic model, this sigma is the covariance matrix of the conditional density. On the right-hand side, we have the forcing term. This forcing term is exactly what you'd expect. It's the mass density times the expected acceleration. Again, this expectation is with respect to the conditional density. So what we've done here is we've derived the mass and momentum conservation equations in the spatial coordinate x. However, these equations are not in closed form, and the reason they're not closed is because we don't know the conditional density nu, which means that we don't actually have a way of computing these expectations, which define this covariance matrix in this forcing function. So the way we get around this is at key points in the domain, we're going to attach to these points a particle method, and we're going to use these particles or these at these key points to approximate the expectations with respect to nu. And then we're going to evolve these particles in time, and we're going to use these particles as a representation of this density nu. So now that we've written down the macro scale conservation equations for mass and momentum, our next step is to write down a time-stepping algorithm which will allow us to evolve our unknown fields in time. So at the beginning of each time step, we're given the mass density and the expected velocity as fields that are defined over the spatial coordinate x, which we've discretized using some finite element-like method. We're also given samples at key points in the domain which define the conditional density nu at that point. So the first step in our time-stepping algorithm is to approximate the covariance matrix sigma and the forcing function f at time step t using the samples at each point in the domain. Given sigma and f, we're going to plug those into this system of equations, the conservation system, to update the macro scale mass density field and the expected velocity u. And then given the updated macro scale field, the last step of our time-stepping algorithm is to use these updated fields to update the samples at key points in the domain, and then just keep applying this time-stepping algorithm over and over and over. So the only thing I need to do to completely define this numerical method is to explain how we're going to update the samples given the macro scale fields. The last step of our numerical method is to define a way to evolve these particles in the velocity coordinate at each of the key points in the domain. So the way we do that is by going back to the original Boltzmann equation, which I've put up on the screen here again. And we substitute into the Boltzmann equation this decomposition for the joint density, where pi, the joint density, is decomposed into, again, the mass density and the conditional density over the velocity coordinate. And then we also will substitute in for the derivative of the mass density. We'll use the mass balance equation or the mass conservation equation to substitute this in for this time derivative. And when we do that, we end up with this equation here, which is an equation for the evolution of the conditional density over the velocity coordinate. So on the left-hand side here, we first have a material derivative, which basically says that the time derivative of each one of these particles and how they'll change in time in this Lagrangian frame is this material derivative. The second term on the left-hand side is the acceleration term, which basically says that the particles are advected around the velocity coordinate by the external acceleration a. And then here on the right-hand side, the first term here is the collision term, which says that the particles at a co-located particles interact with each other based on some collision law. So for example, elastic collision or viscoelastic collision, and that rearranges or changes their velocities based on these interactions. And then this last set of terms here are the relaxation terms. And these relaxation terms, you can think of them as kind of penalizing these particles from deviating too far from the expected velocity. So this first relaxation term basically says that the difference between the particle velocity v and the expected velocity u can't be too large, and the amount of that penalization depends on the gradient of the mass density. And then the second term is a relaxation term that depends on the divergence of the macroscale velocity, which basically says that if the ice is either converging, so you have kind of rafting where particles are jumping up on top of each other, or you have particles or flows being torn apart by some sort of forcing, that you have to account for that in this relaxation term. And these relaxation terms you can kind of think of as a source or sink in this overall equation. And given the solution to the conservation equation, this is a known function. So u and mu, so the expected velocity and the mass density, are known. They're given by the conservation equations. And then this just becomes a linear source term with respect to the velocity coordinate. So now at each point, at each of these key points in the domain, we're going to use this conditional evolution equation to define how these particles will evolve in the velocity coordinate. So they're at a fixed point in space, and they evolve in the velocity coordinate according to this conditional evolution equation. Now I'm going to show some initial results that demonstrate this numerical method to solve the Boltzmann equation. So what you see here is an initial condition where we have the mass density, which is this color map, which we start out with just some constant density in our domain. And as I play the simulation, you're going to see arrows, which represent the expected velocity. And what we have is just a constant forcing to the right, which pushes the mass toward the right. And then as you build up this gradient creates a force that pushes the mass back to the left, and you create this fluid-like sloshing effect, which is what we expect for this simulation. So in the second example, we're going to show some of the benefits of using this kinetic type model versus a more traditional hydrodynamic approximation. What we have here in this example is an initial condition where we have a blob of mass in the middle of the domain, and we're going to apply an external forcing that pulls this blob into two blobs. And so if I run this simulation forward in time a little bit, you can see that what we have is this external forcing, which pulled this blob apart into these two very distinct looking blobs. You'll see there's also a fair amount of diffusion that's happening. That's happening primarily because of the collision operator. So at co-located points or key points of the domain, we have these particles. And in this case, I've prescribed an elastic contact law. So these particles are bouncing off each other, and the fact that they're bouncing off each other creates this diffusion-like effect. But what's important is we're able to kind of pull apart this blob of mass and create two blobs of mass, similar to in kind of a sea ice setting. You might have a large region of ice that's pulled apart, and you have this lead opening up, and this lead would be this center location where you have open ocean. So if I keep playing this simulation, you'll see that because these dynamics are a little too simple for sea ice, we have slightly different behavior than what you'd expect for sea ice. But these blobs of ice get pulled toward the no-flow boundary conditions where they reflect off the boundary. There's a little bit of numerical artifact because I don't have enough artificial diffusion in my hyperbolic solver. But then they reflect off the boundary and they bounce back and they hit each other, and this wave of mass interacts once more. We use the kinetic Boltzmann equation to generalize traditional hydrodynamic sea ice models by replacing the term in the flux matrix that traditionally depends on the effective viscosity with a term that implicitly depends on the flow-flow interaction at the small scale. We derived a complicated numerical method to approximate solutions to our model, but importantly, this method does not require any physical assumptions about the dynamics of sea ice, such as scale separation. Our initial numerical results show that we can capture expected behavior in idealized settings, and our next step is to prescribe a more complicated viscoelastic contact law that better captures the expected behavior of sea ice and model sea ice dynamics on a larger scale. Thank you for paying attention. I'm happy to take any questions either virtually or via email.